All right, hey physics class. I want to go over a few things with you today. We're talking about what circuits are and how circuits work. And just want to review with you real quick here. For a continuous flow of electrons, there must be a complete circuit with no gaps. So when we talk about the word circuit, we're talking about like a whole loop. So somewhere where electrons can go around and continuously flow through. And so that's what a circuit is. We're trying to learn about circuits because they're everywhere in our society today. Technology exists because of circuits, right? Anything that involves electronics, the lighting in your home, electricity in your phone, anything. It all involves circuits. So understanding how circuits work will give us a much bigger picture of how the modern world works. I mean, it's not even that complicated. So that's what we're jumping into today. I want to talk a little bit about just some basics, and then we're going to talk about one type of circuit to look at, and we'll do some practice with it. So, any path along which electrons can flow is a circuit. We just said that, and there's another word here that's important: gap. So, if there's ever a gap in a circuit, that means that the flow of electrons is cut off. They can't cross a gap. So, a lot of times we'll use like a switch like a light switch would be an example that it creates a gap in the circuit. So as long as there's no gaps in the circuit, electrons will flow. But whenever there's a gap, they will be cut off and they stop flowing. So most circuits, especially in your house or in any kind of electronic device, most circuits have more than one device that receives electrical energy. So, like your phone, for example, has a battery that provides all the electrical energy, but then that battery powers all kinds of little devices and little electrical components in that phone. So there's a lot of devices connected to the battery. So these devices commonly connected in a circuit, uh, they're commonly connected in one of two ways, either in series or a parallel connection. Okay, so we're going to talk about those two, and today we're going to talk about the series connection. So it's one way that you can pair up multiple devices in an electrical circuit. And then there's another way, it's called parallel. So we're going to start with series today. And when you connect devices in series, the devices in a circuit form a single pathway for electron flow. Okay, pretty simple, single pathway. The electrons only have one option, they have to go through this path. Now, that's different than a parallel circuit, which we'll talk about later, but there, the electrons can split up and go into different paths and they can choose which one to go into. But for a series circuit, that's what we're talking about today. There is a single pathway. So, for that reason, if there's ever one device that fails in a series circuit, current in the whole circuit ceases and none of the devices will work. So, because there's only one path, and if you cut off one device in that circuit, you've cut off the whole path. So, that's an important part, a difference about a series circuit. If you have one thing go out or one thing get cut off in a series circuit, the rest of the circuit doesn't work anymore. So, let's do an example of this. So if there are three lamps, three light bulbs connected in a series with a battery, they form a series circuit and charge flows through each in turn. When the switches close, meaning whenever the circuit is all connected, a current exists almost immediately in all three lamps. And so this is a picture that I want you to imagine. Like when you have a circuit and you turn it on, it's not that the electrons are all piled up in the battery ready to burst out. It's more like whenever the circuit is connected, electrons are already everywhere because everything is electric. And so whenever you connect the circuit, all of those electrons start moving at once. So electrons don't pile up at any part in a circuit. That never happens. Instead, they all just start moving at the same time simultaneously. It'd be nice if traffic worked like that. Like if there was a green light suddenly, then all the cars started moving at once. But instead, in the real world here, traffic works where the first car has to move first, and then the second car can move. Well, that's not how circuits work. They all coordinate. They all work together. So if you turn the circuit on, they all start moving at once. Um, all right, so here's a very simple circuit. All right, we have a 9-volt battery here, and then we got three light bulbs, and we have a switch. And right now the switch is open, so you can see the switch is up like this. The little metal brown metal part here or gold metal part is not connected, and so you have a gap right there. So these light bulbs are off because there's no flow of electricity through it. Notice what it's saying here. In this simple series circuit, the 9-volt battery provides 3 volts across each lamp, right? So each lamp gets 3 volts. So you add all that up, that's 9 volts total. So if you added more and more lamps, they're not going to get as much voltage the more lamps you add on. So that's something that's interesting about a series circuit. Um, so because of this, because the series circuit works like that, where if you keep adding them on, you get less and less current going through the circuit. These 3 resistors or 3 devices, like the light bulbs in the previous example, they can all be combined and represented by their equivalent resistance. This word equivalent right here, very important word. Equivalent basically just means it has the same value, same amount, but it's not exactly equal. So it's not the exact same thing. When we say equivalent resistance, we're saying basically we can combine all 3. Let me change colors here. We can combine all 3 of these resistors to basically say, well, these are all working together to basically provide one bigger, oh wow, that's bad, one bigger equivalent resistance. Okay, so when we redraw the circuit, and please don't laugh at my circuit here, this is hard to do with a mouse. Or, well, with the, it's not a mouse, it's the touchpad on the Chromebook. This isn't too bad. So when you redraw the circuit, instead of redrawing all 3 resistors, you just want to show their equivalent resistance. And so you can just make one equivalent resistance, and we'll label it R. Sorry about the noise. I have my windows open because it's really nice out. So this one equivalent resistance is equal to adding up all 3 of these. So this equation right here is kind of important. Let me put a box around it. So the equivalent resistance for a series circuit is basically equal to the sum of all the resistors that are present. So it's pretty simple. It's not too complicated there. So add up all the resistors, 1, 2, and 3, like how much ohms they are, and that gives you the equivalent resistance. All right. Oh no, what did I do? Oh, I messed up. Hold on. All right, I lost my drawing tools, but I don't know how to get them back, so we're just going to be stuck like this. That's okay. So coming back, just as a summary here, the voltage drops after each device in a series circuit, and you can calculate how much voltage drops each time it goes by. We're going to save that for later. But here's the summary for today. For a series connection, when resistors are connected in series, which means one after the other forming a single path, there's one path for the current. Every element or every circuit element, every component, every resistor gets the same current found using Ohm's law. So that means that each of these resistors is getting the same current. I mean, could you imagine if that wasn't true? Maybe like the current was going really, really fast through this one, but slow through that one. That would create like a traffic jam problem, right? Because they're zipping by this one, but they get blocked up here. They don't do that. Remember, they all move together at the same time. So that means that every element is going to get the same current. All right, the third part of the summary here, the equivalent resistance is just simply adding up all the resistors together. And then number 4, the voltage drop or potential difference across each device depends directly on its resistance. And we're going to talk about that one more tomorrow. So the main disadvantage of a series circuit is that if one of the light bulbs goes out or if one of the devices fail, then the current in the whole circuit stops. So I don't know if you guys have these Christmas lights like this, but if one Christmas light goes out, like the entire strand goes out, or at least part of the strand. And what that tells you is that all of those lights were wired in series. They're all wired in the same path so that if one of the light bulbs goes out in that path, the whole path is out. That's how some of these light strings work. Now, they design these Christmas lights, the more expensive ones now, so that the whole strand doesn't go out, but maybe part of it goes out. And we can talk about why that is later. But I mean, it's a little bit better than the whole strand going out. So, um, all right. Let me ask you one last question here, and then we're going to do an example. What happens to the light intensity of each lamp in a series circuit when more lamps are added to the circuit? So if you're adding more and more light bulbs, more and more resistors to the circuit, what's going to happen to the light intensity of each lamp? Well, the light intensity of each lamp depends on how quickly the current's going through there. So if you're adding more lamps, you're going to be raising the resistance, right? The more lamps there are, the bigger the equivalent resistance will be, and that'll lower the current. And so each time you add a light, there's going to be less current going through there. So the addition of more lamps results in a greater circuit resistance. This decreases the current in the circuit and in each lamp, which causes dimming of the lamp. So you can't really add a bunch of light bulbs all in the same pathway without providing a lot of voltage because it just makes it really, really dim. So let me do some examples with you guys real quick here. Let me zoom in. There's a part in your book here that kind of gives a summary about how this all works. Um, every time, like down here, you can see a circuit. Every time the current goes through a resistor, the voltage drops, and so it's going to drop twice in this current or in this circuit. And so because of that, you can say that the total voltage is equal to the voltage drop 1 plus voltage drop 2. Substitute in V equals IR, so you can do I1 R1 and I2 R2. Since the current is the same in both resistors, across both resistors, you can factor that out. And basically what you end up with is the total voltage is equal to the current times the equivalent resistance, which is what we expected. So V equals IR, that's Ohm's law, as we've already learned. And so the total current that goes through this resistance or through this circuit, the total current depends on the equivalent resistance and the voltage. So how much equivalent resistance you have and the voltage. So that's an important equation right here. And we've already seen this equation. Equivalent resistance equals R1 plus R2 plus R3 and so on and so on. All right, so let's look at this example. Here you got a 9-volt battery, 4 light bulbs. You can see the resistance of each bulb here. And it wants us to find the equivalent resistance for the circuit and the current in the circuit. So our unknown is equivalent resistance and current. So what can we figure out? Well, it's easy to figure out the equivalent resistance, right? You just add up all of the resistors. So first I want you to draw the circuit. Okay, it doesn't have to look exactly like this. Like it could have one resistor on each side of the rectangle. But anyway, you add up all these resistors. That's pretty easy, right? Add them all up. And so 4 plus 5 is 9. 9 plus 7 is 16. 16 plus 2 is 18. So the equivalent resistance here is 18. So that's what they get on this page. Okay. And then to find the current, you take the voltage and you divide it by the equivalent resistance. Right? I equals V over R. That's another version of Ohm's law. So 9 volts divided by 18 ohms. The current is 0.5 amps. Okay. So that's it. As simple as that. I'm going to have you do these first 3 problems today. So that's what's on Canvas. So let me know if you have any questions on that. I'll try to be checking my email so I can respond to questions that you have. So hopefully that made some sense, and good luck.